around this I've got an electron. Okay? Around this I've got an electron. I want you to compare for me, please, the gravitational force. I want you to solve for me the gravitational force, excuse me, F and G here, holding the electron in orbit versus the electrical force, please. In other words, which of these forces is actually keeping the electron going in an orbit? Now, this is a Bohr model, so it's overly simplified. We know that electrons don't go in nice round circles and everything. You have to go all over the place. But let's make it go in a nice circle, right? What force has to keep the electron in orbit around the atom? Gravity or electric? So please solve for the two. You're going to have to use all the constants there in the packet here for masses and charges.
Radius, north side.
Oh, yeah, we need a radius. Thank you. Let's give ourselves a radius. Well, picometer sounds about right. That might be a little on the small side. We're going to go with it anyway. So we came out with our force of gravity over at 1.4 times 10 to negative 45 newtons, and the electrical force 1.6 times 10 to negative 6 newtons. And that has correct sig figs and units. Now, next thing that I want you to do. This electron, the electrical force is pointing inwards, right? I gave you a radius. Please find the approximate velocity of the electron going around the atom. Please find the approximate velocity of the electron going around the atom. What equation do you have to use? Centripetal force. You have to use centripetal force, right? Whenever you see something orbiting, going round and round and round, I need your head to scream at you centripetal force. Yeah, I need you to just hear. If something's going in a circle, I need something inside of you to yell at you: centripetal force, centripetal force, centripetal acceleration, centripetal acceleration. You've got to hear that. Okay, and you've got to see that. Am I saying that every problem with something that seems to be going in a circle is going to end up going to centripetal force, centripetal acceleration? No. No, I'm not saying all of them, but the thing that governs things going in circles is centripetal force and centripetal acceleration. So if something's turning or going in a circle or makes a quarter circle and you know it continues, centripetal force. Okay, so I would try to anticipate that possibly coming down the road. Right, so like this problem, whenever I drew an electron going around the nucleus here in the atom, we might not have gotten to the second part B, please find the velocity, but you should have been able to anticipate that we might end up using centripetal force to find something else. Okay, so I just need you to be able to anticipate that. So centripetal force, and I'm going to write like we did, sum of the centripetal forces equals m v squared over r. Now, the reason we use sum of the centripetal forces is because it's all the forces going in minus all the forces going out. Okay? All the forces pointing inwards minus all the forces pointing outwards. There's only one real force we have to deal with, and it's pointing in. What is it? Coulombs. Yeah. What? If I didn't have that previous step, in there, you'd end up doing this, right? You'd end up putting in K, M1, M2 over R squared equals M V squared over R. Have we worked problems like this with universal gravitation and orbiting things? Have we worked problems like that? No? We'll go back and do one. We know what all this left side comes out to be then, right? It comes out to be, let's see here, 1.6 times 10 to the negative 6. Equals mass of an electron, 9.11 times 10 to the negative 31st. 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 9.11 that mass of the orbiting thing is the thing going round and round, right? And the mv squared over r is the thing actually doing the spinning. Please make sure you remember that, okay? Velocity is what I'm looking for. V squared divided by, I said, 12 picometers. Is that correct? So that's 12 times 10 to the what? Good, negative 12. Don't get confused at where your squares are. It's centripetal force. It's not radius squared. Okay? It's not radius squared. If you square this guy, everything's all off. So be careful on that. So multiplying over, now it's just working algebra. 1.6 times 10 to the negative 6th times my 12 10 to the negative 12th equals, let's just go ahead and divide that other guy. Working out quickly here, 9.11 times 10 to the negative 31st. And you're going to want to square root that entire thing. Solve over v, so I just worked all of the algebra there at one fell swoop. Okay, I multiplied my 12 times 10 to the negative 12th over. Then I divided my 9.11 times 10 to the negative 31st. And then I just square root it because the velocity is squared. And what does that velocity come out to be, please?
4.6 times 10 to the 6th.
4.6 times 10 to the 6th units, please. Meters per second. Base units in, base units out. Okay? Dang fast. 4.6 times 10 to the 6th meters per second. What's the speed of light? 3 times 10 to the 8th. So as long as we're below that, we're okay. Right? Whenever the electron, by the way, if we were up to like 1 times 10 to the 8th, 1.2 times 10 to the 8th, we're in percentages of the speed of light at that point in time, and relativistic physics kicks in, okay? Which would really throw all this sort of stuff off, okay? Because relativistic physics means that time slows down. So the electron, time would slow down. Or, and whichever way you decide to interpret it, distance shrinks, right? So things would really get wacky with the electron. This is slow enough, though, that it's going really fast, but not really dealing with relativistic physics here, okay? So dang fast, slower than the speed of light. Something can't go faster than the speed of light, so we were all good. Questions about this?